Okay, you have made it to week 14. Yay! This is your last week of learning new material. So, congratulations. After this week, you just have to study for a test and you will be done. Okay, let's see what's happening this week. Oh, as usual, we have an ambitious schedule with lots of concepts here. So let me see if I can get this straight. Looks like we're going to be doing exponential functions, logarithms, I see, solving equations with logs, changes of base. And at the bitter end, we're going to find out why do we need to know all this? And it's so we can work with continuous and compound interest problems. Okay, so let's see what's up on deck here. Okay, we're going to start with evaluating an exponential function that models a real-world situation. Okay, so we see this is a function. There's an equal sign here. Let me see if I can get closer on that. And we have an exponent. So you have an exponent up here. So that's how we know we're working with an exponential function. The dollar value, and they're calling it V of t right here, the value of a certain car model that is t years old is given by the following exponential function. V of t equals 32,000 times, see how they're pressed together with the parentheses, 0.88t. Find the initial value of the car and the value after 10 years. Round your answer to the nearest dollar, and that makes sense since we're working with money. Okay, so let's start with initial value. So initial value occurs when time, or t, is equal to 0. All right, so that's your starting point. Starting point. Let's see if I can get that on the screen there. There we go. Okay, so first we're going to find the initial value of the car. Well, we can substitute 0 in for time and figure out what the initial value is. So let's try that. All right, we're going to figure out what 0.88 to the 0 power is. Okay, so since we're working with exponents, I kind of want to do a little side thing here, uh, just to help you maybe in the future for week 14, you're going to be working with exponents. I'm going to make you a little cheater sheet here that might help. Okay, so let's go with something like, let's go with 2. So 2 to the 0 power, 2 to the first, 2 to the second, 2 to the third, and then we'll go 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. Okay, so when you raise a non-zero number, so 2 is a non-zero number, to the power of 0, the answer is always equal to 1. 2 to the first power is just 2. 2 squared we know is 2 times 2, which is 4, and 2 cubed is 2 times 2 times 2, which is 2 times 2 is 4, 4 times 2 is 8. Okay, 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4, and 2 to the negative 3 is 1/8. And I want you to see if you see a pattern here. So I'm going to put a little box around this. Okay, that's sort of a separator. All right. And then see if you can see a pattern that's kind of happening as we go up in positive exponents and down in negative exponents. Hopefully you're going to see something. So hopefully you see that this 2 to the first power is 2. Well, 2 to the negative first power is 1/2. 2 to the second power is 4. 2 to the negative second power is 1/4. And then 2 to the third power is 8. 2 to the negative third power is 1/8. So you can kind of figure out the pattern there. I'm not going to let you think about that while we move on, but there's a little pattern there. And this, anything to the zero power, any non-zero number to the zero power is always going to be equal to 1. So we're going to use this information because if we raise 0.88 to the zero power, that's just going to become 1. So the initial value, or the starting point, is 32,000 times 1, which is just 32,000. Okay? So your initial value is always right here. All right, now let's figure out the value after 10 years. So we're going to substitute in 10 for time. So I'm going to show you how to do this a few different ways because I don't know what you'll be working with as far as your calculator or if you have a graphing calculator at home, but there's many ways to skin this cat. Okay, let's start off with if you just have a calculator, a smartphone, which most of us have. I'm going to go to the calculator feature on my phone, and then I'm going to turn my calculator sideways, and hopefully it'll click over here. Okay. All right. So hopefully you all can see that. So one way you could do this is turn your calculator sideways, and you could say 32,000. Let's make sure I got enough zeros in there. Times, and I know there's a glare there, so I don't think I can get rid of that glare actually. So I'll try to make that a little crisper. 32,000 times 0.88. Now there's a button on here called X to the Y. So I'm going to click that button, and it's right here, X to the Y. And I want to raise it up to the 10th power. And then I'm going to hit equals. And we have 8912.031. Okay, so I'm going to take that and write that down. 8912.031. So when they want us to tell it then the value of the car after 10 years, you've got the car initially at 32,000, but after 10 years, of course, it's depreciated and now it's worth $8,912. They want us to round to the nearest dollar, so in that case, we're going to call it 8912. Okay, I'm going to show you how to do this on your ALEKS calculator in your homework. So I'm going to hopefully share my screen with you. Okay. Now, here's a little calculator that pops up. It's over here on the right, and I'm just going to use it to help me with this example. So I could type in 32,000 times 0.88. This also has a X to the Y button, so I'm going to click that. And you see how you can see it go up to the 10th power. And hopefully we're going to get the same answer that we got on my cell phone. I just use the ALEKS calculator. Okay, so hopefully that's helpful to you. If you have a graphing calculator, a really nice calculator like this, you could do 32,000. And let me back this up here. I don't know why the glare is so terrible. Let me see if I can do something about that. But not having a whole bunch of luck getting rid of the glare, but here's 32,000. You would multiply it using the multiplication button here. And then I would put 0.88. Ugh, let's see if that makes it any better. We'll tuck it over here. Yep. And then I would use this up button here, up, right above the division symbol, and put 10, and then hit enter. So see, there's 3 ways to skin that cat. I use my graphing calculator, I use my cell phone turned sideways, and I also use the ALEKS feature, the calculator feature. So hopefully that's going to be helpful to you. Pick one thing you could use and maybe a couple different things like the ALEKS calculator and your cell phone and see if you can get one of those or 2 of those to work for you every time. Okay, next up on the buffet, finding a final amount in a word problem on exponential growth or decay. A city has a population of 280,000 people. Suppose each year the population grows by 5.5%. What will the population be after 11 years? Use the calculator provided and round your answer to the nearest whole number. So we're going to use the ALEKS calculator. I'll also show it to you on your cell phone too, because sometimes if it doesn't give you that line, use the calculator provided, then they're not going to give you the calculator. So I want you to have a backup plan. Okay. Um, hmm. So we're going to write out this equation. There's actually two equations I want you to write out. One is called a growth equation, and one's a decay. Okay. And we know we're going to use the growth one because of that word there. So here is an exponential growth equation, and here's a decay. These will come in handy. I recommend putting them on your little cheater sheet or what, the notes you're allowed to take on a test. Okay. So growth and decay, we have a times 1 plus r to the t, and y equals a times 1 minus r to the t. Decay means things are like, you know, reducing. So that's why we use subtraction. Growth, things are adding. Okay. So what are these a's and r's and t's? So a is equal to the initial start amount. T is, of course, always going to be time. That doesn't really change. R is equal to the rate of growth or decay. And you always want to, special note, if it says like 5.5% like it does in our problem, you want to change that to decimal. Okay, so take your 5.5 and divide it by 100 so you can get it into decimal form. You always want to use decimal form. Okay. Okay, so let's write out this little equation. So we know it's a growth. So I'm going to go with y is equal to the initial start amount was 280,000 people. That's our A. In fact, we could write that out. A as a little key is A is equal to 280,000. Time is equal to what they say, 11 years. Rate is equal to 0.055. Okay, so y equals, here's our initial start, A, times 1 plus the rate. The rate is 0.055, raised up to the time, which is 11. Okay, so this is the equation that you're going to use to help answer this question. What's the population going to be after 11 years? So we started at 280,000 people. Maybe this is the population in the Bahamas or something. I'm just making that up. And maybe it's growing at 5.5%, right? This is that 5.5% right here. And after 11 years, how many humans are going to be running around the Bahamas? Okay, so let's find out. So I'm going to start with using my calculator on my cell phone. I'm going to turn it sideways. Hopefully it's going to turn for me. Okay, so I'm going to do 280,000. I'm going to multiply. And then I'm going to do, well, let's add this together. 1 plus 0.055. This is going to become 1.055. Okay, so I'm going to type in 1.055. I'm going to hit that X to the Y button saying I want to go up to the 11 years and hit enter. Okay, that's a lot of people. So they say, I think they asked us to round to the nearest person, which would make sense. So we have 504,585, and 0.87 is going to round us to 86. So we're going to round up to 504,586 peeps. Okay, I'm going to show it to you on the Alex calculator. So I'm going to go back over. Hopefully my screen will go with me. I'm going to hit clear. Okay, so I'm going to do the 280,000 times the 1.055. I'm going to hit the X to the Y, 11 years equals. So that's how we're going to get the 504,586 people. Okay, so hopefully you are feeling better about using technology to help us with these concepts. Next up, find the initial amount and rate of change given an exponential function. Suppose that the future price P of t of a certain item is given by following exponential function. In this function, P of t is measured in dollars and t is the number of years from today. Okay, so we're working with dollars. T is the number of years from today. Find the initial price of the item. Well, we know the initial starting point is A, and we know A is 1400. But remember, initial price is when T is equal to 0. Okay, so when we have this particular exponential function written out, we have y equals, I'm just going to write out the formula for it. All right, and we have y equals 1400 times b to the t. Okay, remember that A is the initial amount when T is equal to 0. It's your starting point. Okay, that's your not poing, starting point. Remember T is time. And then I want to give you a little hint about B. B is like a base, okay? And here's some more little cheater notes that you can put down. If B is greater than 1, then that is equal to a growth equation. Let me make this. If B is less than 1, then you have a decay. Okay, because they're asking us, does the function represent growth or decay? Well, look at your B value. Okay, it's 1.028. 1.028 is greater than 1. 1.028 is greater than 1. Therefore, we have a growth function right there. Okay, by what percent does the price change each year? Okay, well, if we break apart this problem again, P of T, this little equation equals 1400 times 1.028 to the T. And remember what I had you write down on your last slide was something like this. P of T equals A, well, let me make sure I write it exactly like I gave it to you on the last slide so that there's no confusion. For your growth, it was A times 1 plus R raised to the T. Okay, so 1 plus R is what's going on in here. So there's your 1. Your 0.028 is your rate. So we're going to we're going to separate this 1 plus 0.028. All right. This right here is your R. And so we need to multiply that by 100 to get it into percentage. So 0.028 times 100 is equal to 2.8%. So that was what percent the price changed each year is 2.8%. So we didn't have to do any crazy math for that. You just have to kind of look inside of this, know that that piece right there is where your base rate is, separate the 1 from the rest of it. And then once you get that little piece off of there, then that, if you multiply by 100, will give you your percentage. Okay, let's keep going. So the next concept is how to write an equation that models exponential growth or exponential decay. In 2000, a city had a population of 230,000 people. Each year, the population has grown by 8.3%. Let T be the number of years since 2000. Let Y be the city's population. Write an exponential function showing the relationship between Y and T. Okay, let's go back to that basic growth equation or function, sometimes people will call it. Okay, Y equals A times 1 plus R up to the time. Okay, so let's just plug in what we know. The initial start was 230,000 people, so that becomes your A. Times 1 plus, the rate was 8.3. Well, let's change that to a decimal. 8.3 divided by 100 should be 0.083. T is going to be the number of years since 2000. We don't know how long that is, so we're just going to call that T. The last thing you can do to kind of clean this up is to just add the 1 plus that rate, the 8.3%. So you could just finalize this as 230,000 times 1.083 raised to the T. And this is an equation that models the exponential growth. We know it's a growth because this value here is greater than 1, 1.083. We know this is our starting point, 230,000 people, and they're growing by 8.3% each year. So no real math required, just knowing how to put the parts in to this function here. Now, if they had said it was decaying or decreasing, we would want to then revert to our decay function. Okay, they're going to ask you to evaluate natural and common logarithmic expressions. So a log looks like that, and a common log is ln. Okay, so we're going to kind of get into um, natural logs and then just regular logs. I did try to put a little simple definition of what a logarithm is. A logarithm is a quantity that's representing the power to which a fixed number that they call the base must be raised to produce a given number. Another simple way of just saying what the heck is a logarithm is it's the power or exponent to which one base number must be raised or multiplied by itself to produce another number. So, for instance, we live in a base 10 world. We live in a base 10 world. Okay, so we know that 10 squared is equal to 10 times 10, which is 100. So the logarithm of 100 in a base 10 system is 2. The logarithm, that's probably not spelled right, in a base 10 system is 2. And we're going to get into this a little bit more actually in the next video, the second video for this week. Okay, so I've advised that we're going to go into ALEKS because the ALEKS calculator will pop up and allow you to figure out what the log of the square root of 6 is and what the log of 37 divided by 8 is. So I'm going to share my screen and we're going to go back into ALEKS and we're going to find that little calculator feature that they give us. And so let me bring you with me. So let's figure out what the log of the square root of 6 is. Okay, so I'm going to hit clear. Let's pull this down here. And I'm going to hit the log. I'm going to hit the square root. I'm going to hit the 6 button. Then I'm going to put equals. Okay, so I'm going to go out 4 decimal places and call that 0.3891. Okay, so let me stop sharing. So I'm going to go out 4 decimal places. 0.3891. Now I'm going to figure out what the log of 37 divided by 8 is. So I'm going to share my screen. I'm going to clear. I'm going to hit this log button. There's the log. ln is your natural log, which is base e. We'll get to that in a minute here. So 37 divided by 8. We'll hit enter or equals. And we're going to go out 4 decimal places, 0.6651. So right here, 0.6651. So the log button and the natural log button are kind of usually sit next to each other on basic calculators. Natural log is going to be base E. Okay. Well, normally we work in base 10, but sometimes the natural log comes in handy. Okay, what's up next on the buffet? Okay, so I'm laughing because I'm going to show you something. It's probably not going to show up in ALEKS. It's something that I've been kind of teaching for the last 20 years on how to rewrite exponential and logarithmic equations without really kind of like getting too deep into the rules. I call it the circle of love. Okay, you will not see this in a textbook. So converting between a logarithmic and an exponential equation. So they want you to be able to go back and forth. All right. This is a logarithmic equation. We know that because it has a log on it. This is an exponential equation because we know that because there's an exponent but no log. Okay, they want you to write this as a logarithmic equation, and they want you to take this logarithmic equation and write it as an exponential equation. I'm going to start with this one first. So here's how I want you to do it. If you want to, if you want to learn the circle of love, okay? So here's how you say this statement. Log base 2 of the number 16 equals 4. So I'll write that out. Log base 2 of the number 16 equals 4. We're going to write this in exponential format, and here's the circle of love, and it's always backwards, a backwards circle. Or I guess you would call it counterclockwise. Okay, so you're going to start down here with this little 2. This is the base. You're going to put a little arrow pointing to that. You're going to go like that. So see how that's like a counterclockwise motion? So you're going to rewrite this as 2 to the 4th power equals 16. And now this is written as an exponential equation. And 2 to the 4th power does equal 16. That's really 2 times 2 times 2 times 2. Okay. I just wrote a practice one out for you. So think about this one. Log base 3 of the number 9 equals 2. How could I rewrite this? Right, so think about the circle. You could rewrite it as what? 3 to the 2nd power equals 9. And we know 3 times 3 does equal 9. So that's what I talk about when I talk about my backwards kind of counterclockwise circle of love. It also works here, okay? When you have an exponential equation and you want to write it in logarithmic. So you're going to need to give it a log. Give it a log. It doesn't have one, but we have to have a log. And you're still going to use this circle. So I'm going to point just like this with my arrow, the backwards circle. All right, here's how you're going to do that. You're going to rewrite this as, you got to write the word log, and we're going to start here with base 5 of the number 1/5 equals -1. So log base 5 of the number 1/5 equals -1. We know that 5 to the -1 is 1/5. And now we know that the log, when you're working in base 5 of 1/5, is equal to -1. Let me come up with another practice one for you. They always start you off with like a negative exponent, which is not that intuitive. So I'm going to make you one with a positive exponent. All right, here's a practice one for you. 2 to the 3rd power equals 8. I want you to write this in logarithmic form. Okay, so to do that, you're going to write the word log. Base 2 of the number 8 is equal to 3. If you were to go back and try to switch it again, 2 to the 3rd power equals 8. Now I want to show you something too that you need to be careful of. This is not log base 2 and 8's way up here equals 3. That 8 is at the same height as the log. So log subscript or base 2 of 8 equals 3. This needs to be on the same level, all right? Same thing here. This 9 and this log, they need to be at the same height. I think I might have thrown another problem. Yeah, I did. I threw some extra practice in here because these take a little bit of practicing. You can always go and look at the rules on ALEKS of how they want you to do it, but if you don't like that, you're free to use my patented patented circle of love. Okay, rewrite as a logarithm equation. All right, so draw your little backward circle if you're into that. Write the word log. So log base 4 of the number 1 equals 0. And you'll know you're right if you can come back out of this, out of log form and into exponential form. So if you could come back out of it, 4 to the 0 equals 1, then you know you're right. All right, and we know that any non-negatives, zero number, if you raise it to the 0 power, is equal to 1. And we looked at that very early on in the video here. Okay, practice rewriting this logarithmic equation, like get rid of the log and get into exponential form. So hopefully, if you pause the video, you came back and wrote this as 6 to the negative 2 power equals 1 over 36. And they give you little boxes, like over here, this would be log base 4 of the number 1 equals 0. And this would be 6 to the negative 2 equals 1 over 36. Okay, last slide for this video. I'll try to cut these to be less than 30 minutes because, we all have short attention spans. Um, so this will be the last one, and then I'll just finish up the last 5 or 10 slides in the next video. Okay, again, they want us to convert between natural log, this time instead of regular log. So we're going to use ln instead of log. Okay, they still want us to practice converting. You can still use my backwards circle of love, but when you see an E, just know that E goes with natural log. So instead of writing regular log, you're just going to write natural log of the number Y equals 5. And it feels weird, right? E to the Y power equals 5. If we were to rewrite this, right, into exponential format, we would replace ln with E, raise it to the 5th power, and make it equal to Y. Rewrite as an exponential equation. Here we see natural log of x, so you want to get rid of the natural log. You want to replace that with an E. You can still do the circle. This becomes E. Instead of ln, change it to E to the 2nd power equals x. All right, so you're probably going to get some practice in ALEKS on these. Have fun. I'll see you in the next video.